Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 3, Lesson 6. During this lesson, we are going to continue talking about electric potential, otherwise known as voltage. And I would like to remind you that this thing, potential is a noun in this context. And this quantity, potential, is abstract. It's not really concrete. It's not as easy to visualize. So we're just going to keep thinking about it and keep seeing what it means and hopefully getting better at thinking about it. So as we continue to think about electric potential, let me remind you that sometimes there is a charged thing. And if there is a charged thing, so let's pretend there is a charged thing here. Does this charged thing exert forces on other charged things? Yes. So let's say I put another charged thing over here. This one pushes this one to the right. Yes, it is also true that this one pushes this one left, but let's not talk about that right now. It's true. We're just not going to talk about it. Like, it's true that the sky is blue, but we're not going to talk about that right now. It's true that the earth is round, but we're not going to talk about that right now. All we're going to talk about right now is this one true thing, that this one pushes this one right. Now, how hard does this one push this one right? So I'm going to have this purple arrow to indicate that it's exerted by this purple charge. And I know the electric force exerted by this one on this one is K Q1, this is Q1, times Q2, this is Q2, over R squared, where this distance is R. So that is a review. We covered it many videos ago. This equation is called Coulomb's law, that an electric force is equal to KQ1, Q2 over R squared. That's how hard this one pushes this one. Yes, it is also true that it's also how hard this one pushes this one, but we're not talking about that right now. So I want to compare that formula to another formula. So we say that this one creates a field around it just by existing. A charged particle inserts into the space around it an electric field. And we say that the size or strength of that electric field, E, is KQ over R squared. So how big is the field? You know, here, K times this charge over this distance squared. How big is the field right here? Well, it's K times this charge over R squared. And so what you might see is that this part is the electric field, KQ over R squared, KQ over R squared. This is the electric field, and the electric field pushes the charge that I set there. So this looks really similar to this. And then I might also want to know, you know, at any location, this could push on the charged particle. At any location, this could create a field. And at any location surrounding the charge, I could say there is a potential, or there is an electric potential. And the formula for that, at any location, the electric potential is KQ over R. And so what I want to point out is that these three formulas for electric force, electric field, and electric potential are all really similar. If this has an amount of charge Q1, then that Q1, this Q1, that's Q1, and that's Q1. The force it exerts on another charged thing, KQ1, Q2 over R squared. The field it creates is KQ over R squared. So as I go farther away, the field is less. And the electric potential at a location is KQ over R. And so those are really similar. F, E, V. K Q1 Q2 over R squared, K Q1 over R squared, K Q1 over R. And I just want to point out that if you put them together, it makes it easier for me to see what the similarities and the differences are. The one with potential has R in the bottom instead of R squared. The only one that has two Q's is a force, because without putting this charge here, then there's no force exerted. And then I'm just talking about the field exists and the potential exists, but there's no forces exerted because there's nothing to get pushed by the field. So anyway, I feel like these are easier to remember when I set them next to each other. You know that I love to think about units. So the unit for force is newtons. The unit for electric field is newtons per coulomb. And so notice that the coulomb, or the charge, goes away and going from here to here. And that's why, the coulomb appears in the denominator. If what goes away and going from here to here is an R, so notice there were two charges in the numerator, now there's only one, that gave me an extra coulomb in the denominator. Well, then if there's two distances in the denominator and one goes away, then unit-wise, that should give me an extra meter in the numerator, right? If a charge going away in the numerator gives me the unit for charge in the denominator, then the distance going away in the denominator should give me the unit for distance in the numerator. So going from this unit to this unit should be newtons times meters over coulombs. And you're thinking, wait, that's not the unit you said for voltage. Right, I said the unit for voltage was joules per coulomb. But what's a newton meter? It's a joule. So if thinking about the units helps you remember these, that's great too. I just wanted to put those there. Maybe you just want to write them down in your notes with a box around them and memorize the units. Whatever works for you. A little bit more there about electric potential. Now, notice that when I'm talking about this one pushes this one pushes this one in a certain direction. The electric field also has a direction. Potential does not have a direction. Force is a vector because it has a direction. Electric field is a vector because it has a direction. Electric potential, voltage, is a scalar because it does not have a direction. That's worth pressing pause and writing down. So electric potential is a scalar, which actually tends to make your life easier. If this is my coordinate system, and I put 2 coulombs of charge here, and 1, 2, 3, 1, 2, 3, x in meters, y in meters, 1, 2, 3. So I put 2 coulombs of charge there, and if I were to put 6 coulombs of charge here, and I were to say, what is the electric field here at 3,3? Finding the electric field there, it's not that hard. I find the electric field from this one, and I find the electric field from this one, and then I would add those two together as vectors. So I'd have to do vector addition, place them head to tail. It's a lot of work, but it's not that hard. But what if I wanted to find the potential V there? Well, the potential V there, because it's a scalar, V at that location is KQ over R plus KQ over R. And I don't have to add them as vectors. I can add them just as numbers because V is a scalar. So that's 9 times 10 to the 9th. And then I'm going to do Q over R plus Q over R. Q2 over that distance plus Q6 over that distance. Now, still, this distance, what is that distance? 3, 3. So as you know, that's 3 root 2. I hope you remember that from your math class. If you don't, feel free to talk to me later. And then what's this distance? to find the K, Q over R. This is 1, this is 3. So 1 squared is 1, 3 squared is 9, so square root of 10. This distance is root 10. I'm saying this distance is 3 root 2. K, Q over R plus K, Q over R. Boom. Stick it in your calculator and you're done. The fact that potential or voltage is a scalar makes the math on a problem like this easier than adding these two vectors. So that's one of the reasons that scientists like the concept of electric potential. Just makes life easier. So there we go. What I would like to talk about now is a unit for energy. Units. You know I like to talk about units. So energy has the unit, well, we often say joules, but a joule is a Newton times meter, or a kilogram times meter squared over seconds squared. Or the other one I'm about to talk to you about. So joules, Newton meters, kilograms meters squared per second squared are all units of energy. A fourth unit for energy is the electron volt. So it's a lowercase e and a capital V, and it's called the electron volt. And what do I mean when I say electron? Do I mean the size of the electron, the mass of the electron? I mean the charge. So this E means the charge on an electron. So the charge on an electron is 1 coulomb. No. The charge on an electron is 1.6 times 10 to the minus 19th coulombs. Yes. And a volt is 1 joule per coulomb. Remember that? A volt is a joule per coulomb. And the charge on an electron, that's what we mean when we say electron. Its charge is 1.6 times 10 to the minus 19th coulombs. So this coulomb and this coulomb cancel, and I'm left with 1.6 times 10 to the minus 19th joules. So the electron volt is also a unit for energy, but it's a small amount of energy. An electron volt is 1.6 times 10 to the minus 19th joules. And so you might be saying, well, why on earth would I care? The reason we care is sometimes there's an electric field, and let's say that the electric field is, 6 newtons per coulomb. Well, it turns out, I think I told you this before, that 6 newtons per coulomb is equivalent to 6 volts per meter. It is true that 6 newtons per coulomb is the same as 6 volts per meter. Feel free to look at your base unit conversions, and it will show you that. So what if we're going to travel a distance here of 2 meters? Well, if the potential difference is 6 volts per meter, that means this potential difference is 12 volts, right? 6 volts for 1 meter, 6 volts for another meter. So for the 2 meters, it's a total of 12 volts. Okay, so I've got a space here where the potential difference is 12 volts. So what energy as an electron moves from here to here? Now, a positively charged particle would get pushed to the right. So a negatively charged particle gets pushed to the left. So as an electron moves from here to here, it's getting pushed backwards. It's slowing down, slowing down, slowing down. And what I can say is the energy it would lose, how much energy it loses, one electron moves through this potential difference of 12 volts. As an electron goes from here to here, it loses 12 electron volts of kinetic energy. That was so much easier in this weird little unit, electron volts. So you could figure out how many joules of energy it lost, but I'm telling you, it's 12 times that. 12 electron volts. Anyway, fun little unit of energy, the electron volt. All right. Now what I want to talk to you about is a circuit. Do you remember the story last week of the capacitor? And we hooked some wires to it, and we put a battery here. And we moved negative charges around this way. So that is a circuit. And I told you that we could also draw the battery like this, and we could draw the capacitor like that. And it's called a circuit. A circuit is just a space with different elements connected by wires where charges are free to move. So this is a very simple circuit. It is the simplest circuit with a capacitor that we can draw. One capacitor, one battery. But I'd like to talk to you about a different kind of circuit, more complicated. What if instead of one capacitor, I have two capacitors? Ooh, that might be interesting. I wonder what's going on there. Or what would happen if instead of one capacitor, I have a little branch here. So I have a capacitor here. It's terribly drawn. And a capacitor here. And then those two branches come together again. So what would happen if charge were to flow through this circuit? And what would happen if charge were to flow through this circuit? And the answer is different things because these are set up differently. I'm going to tell you the vocabulary for this. This is called a parallel circuit. And sometimes the mouth and the brain don't work well together. This is called a parallel circuit. I'll explain why in a minute. And this is called a series circuit. So things that are, I don't even really know what parallel means other than two parallel lines are crossed by a transversal. But series means one after the other. So I have one and then I have the other. It's like that 7 games thing that happens at the end of the baseball season. They play one game and then they play another game. So I've got one of them and then I have the other. That's what series means to me. And then the other way I could connect these is this parallel way. So let's look at what would happen in those two situations. Let's look at the series one first. I'm going to draw these curves in a more angular way, but I'm taking this picture and I'm redrawing it right here. So I'm going to draw the battery, and then now in a more angular way. Here's a capacitor, and here's another one. So those two are the same thing, just more angles. So what's going on in this picture is I have a negative charge that's being pulled off of this one. It's going through the battery and it's getting shoved on there. Do you see it? And then another negative charge gets pulled off of here and gets shoved on there. And then another one gets pulled off here and gets shoved on there. So I have more positive charges here. Now, when that happens, these positive charges, I'm sorry, goodness gracious. These electrons get pulled off of here. I know what's on here is wrong, so I'm fixing it. As the electrons get pulled off and sent around, what they leave behind is positive charges. And as I shove the negative charges on here, I don't have positive charges there. As I shove the negative charges on here, I have negative charges here. Right? Okay. And so these negative charges on this plate are going to repel the negative charges on the positive plate. And I'm going to press pause for, oh, thank you. I'm just saying thank you to a dear friend. So these negative charges repel these negative charges and they push them away. And as the negative charges leave, they leave these positive charges remaining. And the negative charges end up over here. So what you can see as I zoom in is I have a capacitor with a positively charged in and a negatively charged in, and another capacitor with a positively charged in and a negatively charged in. And what we see is that the charge here, Q, and the charge here, Q, are the same. This number of pluses has to be equal to this number of minuses, because each plus here is because I ripped a minus away and stuck it over there. So when I have capacitors in series, it is a requirement that they have the same charge as each other. That is a sentence worthy of writing down. So I would press pause and write that down. Capacitors in series have the same charge as each other. It's required because where did this charge come from? It came from over here. Okie dokie. So now I know that, whatever this charge is, it's the same as this. So what I could do is what we sometimes wonder, what if I took this battery and I made a little cut right here on the wire, and I made a little cut right here on the wire. And so now I have the same battery. I've just moved the battery down here. It has some voltage V. And now I have this same battery, but I'm not going to hook it up to these two capacitors. I'm going to hook it up to just one capacitor. So this capacitor has a capacitance C1, and this capacitor has a capacitance C2. They might not have the same capacitance as each other, but they have to have the same charge as each other. What we wonder is, what would this capacitance, I'm going to call it C total, this capacitor is replacing these. Now, I could replace this with any capacitance I want, but usually we're saying, I want this battery to have exactly the same experience as this battery. In other words, charge is going to flow, and it's going to keep flowing until it doesn't flow anymore, until this one gets so charged that it's full. It's reached its capacity. This one is so charged that it's full. It's reached its capacity. So I want some capacitor here that's going to cause the same number of coulombs of charge to flow and build up on here as happened over here, so that these two batteries have the same experience. And therefore, this ends up being called an equivalent capacitor. So sometimes I call it C sub T, and sometimes I call it C sub EQ for equivalent. And the question is, what is this capacitance in terms of C1 and C2? Is it C1 plus C2? Is it C1 plus C2 over 2? Is it C1? Is it the square root of C1 times C2? All of which could be plausible suggestions. But I wonder, is there a formula for finding the capacitance? How many farads of capacitance this has to be in order for the battery, once I cut it out of here, to have the same experience when I move it down here. Now remember, by the same experience, Q coulombs of charge moved through the battery. So if Q coulombs of charge move through this battery, I need Q coulombs of charge to move through this battery, which means that this equivalent capacitor, or this total capacitor, should have the same charge on it here as this one and the same as this one. These not only have the same charge as each other, but they would need to have the same charge as this equivalent capacitor, so that same amount of charge flows through the battery. Oh, so that is leading me to an answer, which is good because I'm kind of running out of time. So let's think about that. If I, I'm back. Sorry, I paused real quick because a friend walked in. A friend and brilliant co-teacher. All right. We were comparing this original circuit to this later on simplified circuit, where I said, I want a single capacitor instead of multiple capacitors, but I want this battery hooked up to this to have the same experience as it would have had hooked up to these two. Now, potential is a description of space. So I've got some potential here. And as I cross a battery, as I go, the potential increases. As I go across here, and as I go across here, the potential decreases because I have to get back to the potential that I started at. The potential here is the potential here. So I increase by V volts, and then I decrease and I decrease, and I get back to 0. So this potential change minus this potential change minus this potential change has to equal 0. The potential here is the potential here. So I increase, decrease, decrease, and I get back where I started. I increase by V volts. There's a potential difference here. And if you remember, and I'm going to show you a formula for that and a formula for that. Remember, we said that capacitance is the amount of charge that can be stored per volt. If you go to Crescenta Valley High School, then we say charge is CV. CV, is the name of the high school. Or if you go to Castro Valley High School, where some of my mother's children went to school, but I didn't. Anyway, there you go. Or we could solve this equation for C, we could solve it for Q, or we could solve it for V. When we solve it for V, it's Q over C. So the potential difference across this is the amount of charge Q divided by the capacitance. So Q over this capacitance, C2, Q over this capacitance, C1. So this turns out to be a very helpful equation here. I gain potential, lose potential, get back where I started. I could do the same thing here. I could gain potential V, and then I could lose potential, and I get back where I started for a total change of 0. Here, the potential difference, Q over C, same charge, and now I've got what I call C equivalent. Okay, so how is that going to help me solve for C equivalent? I'll show you. Solve this for V. V equals Q over C2 plus Q over C1. Do you see it? Solve this for V. V equals Q over C equivalent. If V equals this and V equals this, I'm going to set this equal to this. Q over C2 plus Q over C1 equals Q over C equivalent. Divide both sides by Q, and I get 1 over C equivalent equals 1 over C1 plus 1 over C2. And that is an equation that we are going to use over the next few weeks, lots. So what is the summary? When I have capacitors in series, if I were to replace them with a single capacitor, if I want the battery to have the same experience here as it does here, the number of farads of capacitance that this one needs to have is determined by this equation. 1 over the capacitance of this one is equal to 1 over the first capacitance plus 1 over the second. Yay. That's the equation for what we call adding capacitors in series. Now, I'm out of time, but what if I had capacitors in parallel? with exactly the same kind of thinking. C1, C2, voltage. I could replace two capacitors in parallel with one equivalent capacitor, C equivalent. I will leave it to you to think about this in the same way. And actually, this one's a little bit easier. It turns out that the formula for C equivalent is so much easier here. It's just C1 plus C2. The formula for adding capacitors in parallel, I'm just telling you the answer, I'm not proving it to you, is this. The formula for adding capacitors in series is this. I derived this one for you. It's harder. I'm leaving this one for you. Or if you see me in class, feel free to ask. I'm happy to do it for you. And that's all I have for today. So I wish you a wonderful day, and I really hope you don't break any of the laws of physics.